going to talk about the properties of binomial random variables. In particular, the expected value and the variance. But first, we're going to prove this lemma. A lemma is a baby theorem, usually, but not always, a theorem that we would never bother to prove. It's no big deal unless you want to use it in a bigger theorem. In this case, that's what we want to do. We want to use this theorem that I'm about to write to prove what the expected value of a binomial random variable will be. It turns out that r times n choose r, that should be n times n minus 1 choose r minus 1. So to prove this, we compute the left side, we compute the right side, and we show they're equal. R times n choose r, well, r is r, but n choose r is n factorial divided by r factorial times n minus r factorial. N times n minus 1 choose r minus 1. Well, this is not n factorial, excuse me. It's n times n choose 1, sorry, n minus 1 factorial over r minus 1 factorial. Now, to figure out the difference between n minus 1 and r minus 1, I mean, if somebody asks you what's the difference between 22 and 14, if you choose, you can add, say, 6 to both numbers. Now you want to know the difference between 28 and 20, which hopefully you might see as 8 more easily. Okay, you can add and subtract the same amount to each of the two numbers you're subtracting and get the same exact answer. Somebody asked me how many numbers are in between 23 and 12. Let's make it 28 and 12. You know, I would probably take away 11 from both. Well, let me not write it this way. From 12 to 28. You read page 12 all the way through and including page 28. How many pages did you read? Well, I know one thing. If I read from 1 to 9, I read 9 pages. If I read 1 to 19, including 19, I read 19 pages. 1 to 194, I mean, why not just take away 11 from both and say I'm going from 1 to 17? Now, why am I going off on this? Because we need to figure out what n minus 1 minus r minus 1 is. We need to figure out what this number minus that number is. Well, if I add 1 to both of them, the top number is n, and the bottom minus the bottom number is r. Okay, so you don't have to go through, minus 1, we're subtracting, it's 0, n minus r. But I know a lot of you would even go further. N minus 1, you take away r, you'll take away minus 1, which means you add minus 1. The ones are going to cancel. Okay, now somehow I want to show that these two are in fact equal. I want to show that these two are in fact equal. Well, I notice an n factorial here, and what do you know? N times n minus 1 factorial is n factorial. So that's in common. And I have r minus 1 factorial in the bottom. I have n minus r factorial in the bottom. Well, the n minus r factorial is common. And then I say, oh yeah, if you take r and you divide it by r factorial, you're going to have r minus 1 factorial in the bottom. N factorial won't change. N minus r factorial won't change. If you want to see this in greater detail, r factorial is r times r minus 1 times r minus 2, all the way down to 3 times 2 times 1. And there's the r like it should be. Well, r over r cancels out to 1. So now you have 1 over r minus 1 times r minus 2 times r minus 3, etc. But that's just r minus 1 factorial, which is exactly what I put on the bottom. So it turns out that these two are the same. That is, this and this are the same. The theorem or the lemma has been proven. Okay. Now, let's attempt to calculate the expected value of our binomial random variable. Now, since we want to find the variance, since we want to find the variance of x, which is e of x to the second minus e of x quantity squared. That is, we want e of x to 1 power and e to an x over e of x to a second power. That second power is not a very exciting one. It's just the number 1. But nonetheless, we want e of x to 2 different powers. So, rather than doing these two probabilities, these two expected values twice, that is, calculate e of x squared and then calculate e of x, why not just calculate e of x to the k, and then in the end, we'll let k be 2, and we'll let k be 1. Well, by definition, this is a summation of, I'll use the letter r, of r to the k, I'm letting x equal r, so it's r to the k times the probability of r. And I should have said it, but the parameters, the parameters are n and k. That is, we are doing this experiment n times. Okay? We're doing this experiment n times. Okay, since it's binomial, so most of this stays the same, or some of it stays the same, but since it's binomial, I know what p of r is. Since this experiment is being done n times, it's n choose r, p to the r. I'm going to use a different notation. Instead of writing 1 minus p, it's customary in probability theory to just call it q. And that's the power of q is going to be, like always, n minus r. N minus r. Okay. Now, we have that little lemma that r times n choose r is n times n minus 1 choose r minus 1. So, I have their n choose r, but I don't have r in front. Or, I'm not multiplying by r. I'm multiplying by r to the k. So I'm just going to break off one r. R goes from 1 to n. I have r to the k minus 1 times r. That's r to the k. Times the rest. N choose r, p to the r, q to the n minus r. Okay. I'm going to factor out 1p. But first, let's deal with this. Okay, actually, maybe I lied. First, I'll write this down. R to the k minus 1. r times n choose r. This is that. I'll put the n in the front, and the n minus 1 choose r minus 1 inside. After all, that's a function of r. N minus 1 choose r minus 1 is a function of r. I'm going to pull out one of the p-values, because somehow I know, and I don't know how they do this the first time, but we know that the expected value is going to be np times something. So I pull out 1p, and I'm left with p to the r minus 1 times q to the n minus r. Okay, let's get rid of this on the bottom. Let's try that a second time. All right. Now, what we want to do here is make some substitution change. We want to let j be r minus 1. So I have the np. I'm basically copying this down now. I have np times the summation. Well, if r starts at 1, so I want to put j here instead. If r starts at 1, 1 minus 1 is 0. That is, j will start at 0. And if r finishes at n, n minus 1, that's where j is going to finish. N minus 1 choose r minus 1 is j. It says r minus 1, we put j. P to the r minus 1, that's p to the j. Q to the n minus r. Well, adding 1 to both sides, we learned that r is j plus 1. J plus 1, which makes the power m minus j minus 1. So we have that now. Okay, so let's see what we do. Now, I take it that I forgot to comment on that. That's just r to the k minus 1. That is just r to the k minus 1. So let's write down neatly what we have. np, the summation as j goes from 0, not to n, but n minus 1. We have r to the k minus 1. N minus 1 choose j. Now, let's look at all of this. This here is going to be binomial because I have p to the j, and then I have 1 minus p, if you prefer, to the n minus 1 minus j. N minus 1 minus j. Let me write it that way. So that part, that's like p, that's like the probability that x equals j. Now, one last comment. R is j plus 1. So let me put that here. R is j plus 1. Now, it's NP. Now, everything else is j plus 1 to a power times the probability. This is just the expected value of y plus 1 to the k minus 1 to the k minus 1. Think about it. You really need to be able to handle that one. So now, that's the expected value of x to the k. That's the expected value of x to the k. Going to write that down. our result down, and then we'll deal with things from there. We've just proven that e, the expected value of x to the k, is nothing more than n times p times the expected value of y plus 1 to the k minus 1. Well, if I let k equal 1, then I'll have x to the 1 or x. That is, I have e of x, the expected value of x. And this is np times the expected value of y plus 1. 1 minus 1 is 0. Well, that's just the expected value of 1. Y to the 0 is 1, which is just 1. The expected value of a constant is just the constant. So you always get a 7 on your test. On your test, your average will be 7. If you always get a 1, it's 1. So np times 1 is just np. So we just learned something. The expected value of a random variable x, the expected value of x, is just n times p. And we'll look at some examples, and you'll see that that makes sense. E of x squared. Just put 2 in for x. Just put 2 in for x. It is np times the expected value of y plus 1 to the 1, which is y plus 1. Now, remember, the expected value of x plus a is just e of x plus a. It's just e of y, which is np. So we have np times np plus 1. With one exception. It's n minus 1. It's n minus 1. Earlier we had the well, let's just go to it. The power, the largest value j can be is n minus 1. So e of y is, quote, the n value, the upper limit. You have to start at 0, and you go to that upper limit and multiply it by p. It's n minus 1 times p plus 1. Plus 1. Okay, so it's the upper limit, n minus 1 times p, and then plus 1. Plus 1. Which turns out to be, so let me erase some of this on my physical board. It's a lot of letters, etc., but this is what probability is. Okay, so we have this, which is np times distributing np minus p, np minus p plus 1. That's e of x squared. So now, the variance. The variance of x is simply e of x squared, something we just computed, minus e of x, something else that we already computed, squared. E of x squared is np times np minus p plus 1, minus e of x is np squared, that is times another np. Between here and here, I can factor out np. I factored that out. So what's left is np minus p plus 1 minus np. So this np cancels out, and we have np. Instead of saying minus p plus 1, we'll say 1 minus p. Here's 1, and I'm taking away p. This here is the variance of a random variable x. You multiply n times p and multiply that by q. n, p, q. Q is 1 minus p. So the expected value of a binomial random variable is n times p. So why don't we do a couple of examples to calculate the expected value and the variance. Nice type of problem to do would be a coin problem. You toss a coin a certain number of times. Suppose you toss a coin 50 times. Toss a biased coin 50 times. Bias just means that, and this is not the usual probabilities. Suppose the probability of getting a head is a little bit less than a half. It's not 2 out of 4, but it's 2 out of 5 times. And the probability of getting a tail is 3 out of 5. Normally, if you toss the coin 5 times, in the long run, you get 2.5 tails and 2.5 heads, not 2 heads and 3 tails. And suppose we defined a random variable x to equal the number of heads. Okay, what is the expected value? What is the expected number of heads to come up if you toss the coin 50 times? Well, 2 out of 5, multiplying top and bottom by 10, is 20 out of 50. You would expect 20 heads. And for the record, 3 out of 5 is the same as 30 over 50. You toss the coin, this particular coin, 50 times, you'll get 20 heads and 30 tails. So the expected value of the number of heads should be 20. The formula works like a charm. It's NP. N is the number of times you do the experiment, 50, times the probability of success. Success is heads, and that's 2/5. 2/5. Well, 5 goes into 50 10 times. 10 times 2, 20. Exactly what we said we would get. For the record, the variance of x is NPQ. Now, don't reinvent the wheel. We already know what NP is. It's NP, 20, times Q, which is the probability of not getting a head. That is the probability of getting a tail. 3/5. Turns out that 5 goes into 24 times, 12. And if I asked you for the standard deviation of x, other than simplifying, it's very simple. It's just the square root of the variance. 12 is 4 times 3. The reason I picked 4 is I know the square root of 4 times the square root of 3. It's 2 square root of 3. So we calculated the variance, the standard deviation, and the expected value. So just to be formal, the standard deviation of x, well, it's the variance, NPQ, but it's the square root of that. That's the formula to calculate the standard deviation for a binomial random variable. It has to be binomial. It It's not any old random variable, but a binomial one. Let's try one more. Now remember, for binomial, there should be two outcomes, this or that. That does not mean you can't do a dice problem. You can do a dice problem. Suppose you roll a die 30 times. Suppose you roll a die 30 times. Now, when it comes to the random variable, there can only be two outcomes. Let the random variable x count the number of times 1, 2, 3, or 4 comes up. So let x equal, so the probability that x is equal to 1, which is 1 through 4, well, it's 4 out of 6, or 2/3. Let's call x equal to 0 if you get a 5 or a 6. And this is 2 out of 6, or 1/3. So either you get 1 through 4, or you get 5 through 6, 5 or 6. It's one or the other. We made it our binomial. Okay, you really hated what I just said? Well, there's another way of viewing this. The die has 6 sides. The die has 6 sides. Color 4 of them. 1, the bottom here. Side number 2, the bottom. This side, number 3, and maybe the top, number 4. Paint them blue. Paint them blue. And then, or maybe I should say black. Okay. And now you can paint the back and the front red. Okay, now roll the die. There's 2 outcomes. You either get red or you get black. Red or black. So it really is 2 outcomes. Even you can have 2 outcomes even with a die. Okay, so what is the expected value? What is E of x? The expected value of x. Well, if you throw this die 30 times, you can multiply top and bottom here by 10. Oops. Or you can multiply top and bottom here by 5. Either way, 20 times out of 30, you're going to get 1 through 4. So the answer should be 20. And the question is, do we get 20? The formula says it's NP. N is the number of times you do this experiment, which is 30 times, and P is the probability that you get 1 through 4, which is 4 over 6, or if you prefer, 2/3, 4 over 6. 6 goes into 30 5 times, had 5 in my mind, and 5 times 4, yep, it's 20. What's the variance of x? Well, it's NP, which is 20, times Q. It's 20 times Q. Q is 1/3. So it's 20 times 1 over 3. And the standard deviation of x would be the square root of 20/3. Let me please clean that up here. It's the square root of 20, which is the square root of 4 times the square root of 5 over the square root of 3. I know the square root of 4, that's why I broke 20 up to 4 times 5. Not 2 times 10. Don't know the square root of 2, don't know the square root of 10. Now one other thing, I don't like square roots on the bottom, so I'm going to multiply by 1. And why did I pick square root of 3 over square root of 3? Very simple reason. The square root of 3 times the square root of 3 is 3. It doesn't have any square roots anymore. Square root of 4 is 4. The square root of 5 times the square root of 3 is the square root of 5 times 3. 5 times 3 is 15. And 4/3 does not reduce, so that is the standard deviation. 4 square root of 15 divided by 3. So it does make sense that the expected value of a binomial random variable is nothing more than n times p. And we prove that you multiply that by q, you get the variance. Okay, that completes this section. Just multiply n. If you have a binomial random variable and you're given n and p and you're asked to find the expected value or the variance, just multiply n times p or n times p times q.